Welcome to Episode 7 of A Visual Approach to Optics, a Guide for Clinicians, narrated by Dr. John Gorfinkel. In the last episode, we completed 160 out of 278 slides. In the last episode, we finished with this slide, which showed the formula for calculating magnification of an afocal telescopic magnifier. Here we see that if we have a -20 diopter eyepiece lens and a +10 diopter objective lens, the magnification will be 2 times. The number is positive, indicating that the image is upright. In the case of an astronomical telescope, where the objective is positive and the eyepiece also positive, we have numbers of +10 and +20 here, would have given a magnification of -2 times, in which case the image is also magnified but inverted. What happens if we use a telescope to see near objects instead of distant ones? Here we have an astronomical telescope with a +10 diopter objective and a +20 diopter eyepiece. Instead of having an object far away, we have a near object with divergent light. Instead of getting an afocal magnification, we have a different situation. This is nothing more than the multi-lens system in which we have incident light giving off image light, which becomes the object for the second lens. Here we have the image point created by the first lens if the second lens were not there. The first lens here and the second lens here. But with the second lens in place, the final image has been shifted. Doing the calculations for an object that's 20 centimeters in front of the objective, we end up with a real image which is located here in this diagram, so that an observer who is about 1 centimeter behind the eyepiece will have to use 36 diopters of accommodation in order to see it clearly. This is well beyond the human capability to focus on near light, showing that when trying to use a telescope for near objects, we do not get a clear image. We can, however, convert a telescope into a microscope by adding a lens in front of the telescopic system to convert divergent light from a near object into non-vergent light that will then enter the telescopic system and undergo afocal telescopic magnification. In order to have non-vergent light leaving the additional lens, known as a cap lens, we need to position the object at the primary focal point of this lens, which in effect makes this lens a simple magnifier, which is the power of the lens divided by 4. If we take that number and multiply by the afocal telescopic system magnification, we get an overall total magnification of the system. A slit lamp and an operating microscope are examples of microscopes. The distance between the object and the first lens is known as the working distance and can be adjusted by the power of the lens that we have here. In the case of a slit lamp, the working distance tends to be 10 centimeters, and in the case of the operating microscope, it is generally adjusted for 20 centimeters or 200 millimeters, which allows more space for the hands to work between the patient and the microscope. Here are the optics of the slit lamp and operating microscope. We have the object, the cap and objective lens here, and the eyepiece here. In between, in the case of the slit lamp, we have an additional Galilean magnifier, which is controlled with a lever. This additional magnification can be swung in and out of the optical path for additional magnification if wanted. Because we have positive lenses in the objective and the eyepiece, this is an astronomical telescope, which would give inverted images, except that we use inverting prisms here to invert the image. Here we show the magnification of glasses versus a contact lens in correcting myopia. The patient has an eye error which is positive. In other words, the overall optics of the eye are too strong for the length of the eye so that the image would be focused in front of the retina, if not for additional lens correction placed in front. In this case, we have a minus contact lens. Here we have minus glasses, which are located at a certain distance away from the eye, as compared to the contact lens, which is right on the eye. Although both situations correct for the myopia, they have different optical qualities. In the case of the glasses, we have created a reverse Galilean telescope, in this case minifying images, as compared to the contact lens. As long as the image is at the secondary focal point of the correcting lens, and this secondary focal point is also the far point of the eye, this point will be conjugate with the retina and the image will be clear. While these two setups are equivalent for clarity, for distance vision, they are not necessarily equivalent for objects that are close by. Here we have a situation where we correct hyperopia in which the eye has a minus eye error, insufficient power to focus the light on the retina. The light is focused further back. With the addition of a plus lens to compensate, the image is focused more in front and on the retina. As long as the image point is at the secondary focal point of the correcting lens, and this point is also the far point of the eye, this point will be conjugate with the retina and the image will be seen clearly. The contact lens here, or the glasses over here, will both correct the vision and allow a distant object to be seen clearly. However, the glasses will create a Galilean telescopic effect, in this case, magnification effect, as compared to the image seen when using a contact lens. Here we see an object that is far away being focused by the correcting lens so that the secondary focal point is here, and this point now becomes the far point of the eye and is conjugate with the retina. This far point is shown to be 0.1 meter in front of the eye. Here we have an equivalent situation where the correcting lens is 0.02 meter in front of the eye and therefore 0.08 meter from the far point. The minus 10 diopter lens has a secondary focal point 0.1 meter away. In order for this lens to focus light at this level here, 0.1 meter in front of the eye, which is 0.08 meter in front of the lens, this lens would have to have a power of minus 12.5 diopters. In other words, a minus 12.5 diopter correcting lens at 0.02 meter in front of this eye is equivalent to a minus 10 diopter lens on the eye. In both of these diagrams, the eye is shown to have a plus 10 diopter eye error, which can be corrected either by placing a minus 10 right on top of it, or a minus 12.5 in front, 0.02 meter in front. The difference is in the telescopic effect. In this case, a reverse Galilean telescope, which adds minification to the image. The image will be clear over here, just as it is over here, but it will be minified. One can consider the eyepiece here of plus 10 and the objective here to be minus 12.5. Using this formula, one would get 10 divided by 12.5, which is 0.8 times magnification, which is minification. And it is a positive number overall because of the formula, which indicates the image is upright. Here we calculate the magnification using glasses to correct the hyperope. In this case, the hyperope has -10 diopters eye error, which can be corrected with a +10 diopter contact lens on top of the eye, or with a +8.3 diopter lens at 0.02 meter in front of the eye. The correcting lens here has its secondary focal point 0.1 meter behind, which is at the far point of the eye. Over here in this eye, the lens is an additional 0.02 meter in front of the eye, and the far point of the eye is still 0.1 meter behind the eye, so that the total distance of this lens is now 0.12 meter from the far point of the eye. This secondary focal point of the lens requires that the lens have a power of 8.3 diopters, which is lower than the lens at the plane of the eye. Once again, we can calculate the magnification effect. In this case, the eyepiece here, -10 diopter eye error, and the objective plus 8.3 gives a total of 10 divided by 8.3, which is 1.2 times magnification. The number is positive, which indicates an upright image. So in general, when using plus lenses in front of the eye, one gets magnification. When using minus lenses in front of the eye, one gets minification when compared to using the corresponding contact lens option. In order to calculate the correcting lens power at any vertex distance, which means the distance between the eye and the correcting lens, we need to know what the eye error is, and then we can calculate where the far point is. If this eye has an eye error of +10, that means that the far point of the eye will be 0.1 meter in front. In this case of the hyperope, the -10 diopter eye error requires that the far point be 1 meter behind the eye. Once we know the vertex distance between the lens and the eye, we subtract that here from the distance of 0.1 meter, and we get a new distance, in this case 0.08 meter. This distance has to be the secondary focal point of this lens, so we can take the inverse and calculate the power that this lens needs to be. Similarly, in the case of the hyperopic eye being corrected, we know where the far point of the eye is because the eye has a -10 diopter eye error, 0.1 here. Once we are given the vertex distance between the lens and the eye, in this case we add the two numbers together. In order for this lens to have a secondary focal point 0.12 meter away, we take the inverse to calculate what the power of this lens needs to be. As we have done earlier, we showed that this minus lens example is -12.5 at 0.02 meter, and this plus lens example is +8.3 at 0.02 meter in front. Having said that these two types of corrections are equivalent is only true when looking at objects that are far away, in which the incoming light is non-vergent. When the object is nearby and has divergent light, we have a different situation, in which the overall effects are not identical for seeing an image clearly. Basically, we need to treat this as a multi-lens system calculation where we have a U1, P1, and V1 and a U2, P2, and V2. The overall result is that more accommodation is needed with the contact lens than the glasses in this situation once one works through all the numbers. In other words, the overall effect with the glasses is that one needs 3.3 diopters accommodation to see an object that is 0.2 meter in front of the eye. In the case of the contact lens, one needs a 5 diopter correction in order to see an object that is 0.2 meter away. It is easier to understand the contact lens situation because the object has a -5 diopter divergence when reaching the eye because it is 0.2 meter away. We add the -5 divergence to the power of this minus lens and we get -15 coming in at the eye. Since the eye error is +10, in other words it has built-in +10, the -15 plus 10 leaves -5. In other words, there's 5 diopters missing, and the eye needs to accommodate the extra 5 diopters. It is somewhat less intuitive to come up with the total calculation here, but if interested, you can look at how it is done, and the overall effect is a 3.3 diopter accommodative amplitude required to see this same near object with this setup. Here we see how various spectacles magnify images. We have an original circle, which is being viewed through a spectacle lens. This +5 diopter lens is magnifying all meridians equally, and a magnified circle is seen. Here we have an additional 2 diopters at 90 degrees, so that there is extra horizontal power. The magnification is greater in the horizontal meridian, resulting in the appearance of a horizontal oval as compared to the original circle on the wall. Here we have a similar cylinder but tilted at 135 degrees so that the magnification is greater at 90 degrees away in the 45 degree meridian, and we have a tilted oval. Here we see how unequal magnification by glasses affect images. We show from the patient's point of view each eye viewing a circle on a wall and the appearance that the left eye sees and the right eye sees. In this first pair of glasses, we have a 2 diopter lens on the left and 5 diopter on the right. The left eye sees a less magnified image than the right eye. If the images are too different in size, then one is going to get diplopia. In the second pair of glasses, we have an astigmatic lens with more horizontal power than vertical power. There is more magnification in the horizontal meridian than the vertical, equally in both eyes. Both eyes together then see a horizontal oval. In the third pair of glasses, we have a 2 diopter spherical lens over the left eye and an astigmatic lens with greater horizontal power over the left. The left eye sees a somewhat magnified circle. However, the right eye sees a horizontal oval. Because each eye is seeing a different type of image, the brain may either fuse the images or have double vision. Where the disparity is in the horizontal meridian, if it is not too large, it is possible for the brain to fuse them and create false stereopsis. Here we see how stereopsis works. First, we need to understand that there are corresponding retinal points of each eye, so that points on the temporal retina of this eye correspond with nasal retinal points on the other eye, and similarly nasal points on this eye have corresponding temporal points on that eye. Where an image is simultaneously focused on non-corresponding points, say in the temporal side of each eye or the nasal side of each eye, one may either see them as 3D or as diplopia, depending on the degree of disparity. If we have the eyes focused on a single point here so that it is aligned with the fovea of each eye, the eye is looking here at this white point on the surface of the box, there are points which are both further away and closer to the eye. Points that are closer to are focused on non-corresponding parts of the retina that are in a more temporal position. We call this bitemporal disparity. Points that are farther away have binasal disparity. It is possible that one can create such disparities using unequal magnification of images to each eye. in which case one would get a sense of false stereopsis. Here we see a model of false stereopsis caused by unequal meridional magnification. From the patient's perspective, looking at a circle on a wall with unequal lenses, we show a circular image seen by the left eye and a horizontal oval image seen by the right eye. In this case, the point X, which is on the temporal retina of this eye, has a corresponding point on the other eye which is shifted more nasally than it should be because of the horizontal magnification. Similarly, the point O here on the circle, seen by the left eye, has a shift towards the temporal side more than should be by the horizontal magnification on the right side. In other words, the point X here is shifted more nasally and the point O here shifted more temporally in front of the right eye by this unequal meridional magnification. Because the X is shifted towards the nasal side of the visual field, this means that it is shifted more on the temporal side of the retina, since images are inverted and everything is opposite on the retina as on the visual field. This creates a bitemporal retinal disparity of the point X, which is therefore seen as closer. Similarly, this analysis would show that the point O suffers a binasal retinal disparity and is seen as farther away, whereas the circle on the wall has the points X and O as shown. The combined image seen by the brain would be of a circle which is tilted around a vertical axis in and out of the page. In other words, the point X is on the part of the circle seen as closer, whereas the point O is on the part of the circle that is seen as farther away. In this way, the unequal meridional magnification here has created false stereopsis of this flat circle on the wall, in that it is seen as a circle that is rotated around this axis shown. This assumes that the bitemporal retinal disparity of X and the binasal retinal disparity of O are within an area called Panem space, which is an area in which the brain is able to fuse them to create the sense of stereopsis. Should the disparities be beyond the capability in Panem's space, they would be seen as diplopia. The ability to fuse the images into a single stereoscopic images applies in the horizontal meridian. If there were a retinal disparity in the vertical meridian, this would not be possible, and diplopia will most certainly result. The importance of this finding is that when prescribing glasses of different meridional magnification in each eye, it is possible for patients to perceive objects to be tilted where they really aren't tilted and to have difficulty using them, a condition called anisoconia. Here we see the magnification effects of high plus lenses. We know that plus lenses magnify images relative to the true size of objects seen. So here we see the visual field seen by a patient through the spectacle glass. Here is the perimeter of the spectacle and the visual field seen within it. Because the space behind the lens is magnified visual field, the original visual field demarcated here is expanded to fill the entire space over here. In other words, there's an area in between the original and magnified images which is covering up a ring of visual field that becomes invisible. We call this a ring scotoma, which is a donut-shaped area of field obscured by the expanded image space behind the spectacle plus lens. As one moves one's head from side to side, it is possible for objects to suddenly jump out of the ring scotoma or suddenly enter the ring scotoma, which creates disturbing effects. These effects are more noticeable in the high plus spectacle range above +5 or +10. In the days before lens implants with cataract surgery, patients wore aphakic spectacles that were routinely in the +10 and higher range with a significant ring scotoma effect. This jumping in and out of images into and out of the ring scotoma is called the jack-in-the-box phenomenon. Chapter 5. Vision Tests and Optical Instruments. Here we see how to measure vision using optotypes. The minimum resolvable visual acuity is 1 minute of arc. 1 minute is 1/60th of a degree. An optotype typically has 5 minutes of arc with segments of light and dark of 1 minute of arc each. The minimum resolvable optotype is 5 arc minutes, and the minimum resolvable components are 1 minute of arc. We can describe this as MAR of 1, or log of MAR equals 0. We can describe it as Snellen acuity equals 6/6. 6 meter here is the testing distance, and the second 6 is the distance from which a normal person can see that letter. Therefore, 6/60 meter would indicate that at a testing distance of 6 meter, the patient can only see what a normal-sighted can make out at 60 meters away. This would be a larger letter, and if that were the minimum angle of resolution, then that would be reduced visual acuity. We could describe it as cycles per degree. Each cycle is made up of a light and dark component of 1 minute of arc, so that total cycle has 2 minutes of arc of visual angle. Since there are 60 minutes of arc in a degree, there are 30 cycles that are 2 minutes of arc in size. So a CPD of 30 is equal to an MAR of 1. We can measure vision using different scales. So an MAR of 1 is like a Snellen acuity of 20/20 using feet, or 6/6 using meters. Since MAR equals 2.5 m, the M scale would have 0.4 is the same as MAR of 1. Using a font size of 3, a typical reading distance would be like an MAR of 1. Log of 1 is equal to 0. Logmar is 0. The decimal is the inverse of the MAR, so that it would still be 1. If the MAR were double, in other words, vision were half as good, so that the minimum angle resolution is 2 minutes of arc, the vision would be 20/40 or 6/12. M would be 0.8 instead of 0.4. The font size would be, minimum font size would be 6 instead of 3. Log MAR would be 0.3 instead of 0, and the decimal would be 0.5 instead of 1. This 0.5 is sometimes described as 50% of normal vision. The contrast sensitivity is shown here of a typical person at this age. The log of the contrast sensitivity on the y-axis and the spatial frequency or size of the object on the x-axis, which can be described as cycles per degree, or the equivalent Snellen, which would be 20/120 here, or 20/40 here, or 20/30. It turns out that the maximum contrast sensitivity is of an object that has a visual angle of light and dark overall of 4 cycles per degree. And smaller objects up here require higher contrast to be seen than the somewhat larger ones here. This area of 4 cycles per degree is said to be the size of the light and dark bands of the human face seen from a typical distance away of about 3 to 6 meters. This is supposed to be teleologically advantageous in identifying other individuals in dark lighting.